Hello and welcome to the GCSE Science Tutor. Today we're looking at Lesson 8, Isotopes. So let's first recap the atomic structure of chlorine. Using the symbol on the right, calculate the number of protons, neutrons and electrons. Pause the video now and I'll go through the answers in a moment. So the atomic number of chlorine is 17, and this is the same as the proton number. So the number of protons of chlorine is 17. There are 17 positive protons, so we must also have 17 negative electrons. To work out the neutron number, we must take 17 away from the mass number, which is the top number, of 35.5. So we simply do 35.5, take away 17 to give us 18.5 neutrons. In the previous task, it looked as though chlorine in fact had half a neutron, 18.5 in total, but this is in fact not the case. Chlorine actually exists as two isotopes, and what that means is that two chlorine atoms actually exist in the universe. Some chlorine atoms have 18 neutrons, and some have 20 neutrons. So in fact, they exist as isotopes. An isotope is an important definition that I suggest you note down. It is where atoms of the same element have the same number of protons, and therefore the same atomic number, but different number of neutrons, and therefore different mass numbers. So why does chlorine on the periodic table have a mass of 35.5 and not, say, 36? Which falls in the middle of the two mass numbers of the two isotopes? Well, that's because of their abundance. The abundance means how common they are in the universe. And in fact, chlorine 35 is 75% abundant, and chlorine 37 is 25% abundant, which means how common it is. And mathematically, if we were to take an average of these numbers, we do not fall bang in the middle at 36. Because chlorine 35 is more abundant or more common, the average leans towards the number 35, and we can show this mathematically. To work out the relative atomic mass, we need to do the following calculation. Relative atomic mass equals, well, we first take the mass number of 35 of the first isotope, and we multiply by the percentage abundance of 75, place it in a bracket, and add it to the mass number of the second isotope, which is 37, multiplied by its percentage abundance, which is 25. And we can then divide that by 100, put that in our calculator, and we will find we get the answer of 35.5, which is exactly the same number as what we find on the periodic table, which we can see here. So let's take another example. Let's look at carbon. Now, carbon doesn't exist as a single isotope in the universe. In fact, there are 3 isotopes of carbon. We have carbon-12, carbon-13, and carbon-14. Each still carbon because they have 6 protons, which makes it carbon, but their number of neutrons are different. Their abundance is important for working out the relative atomic mass. So in fact, carbon-12 has a 99% abundance, carbon-13 0.9%, and carbon-14 is not very common or abundant at all at 0.1%. So let's show mathematically why the periodic table has a relative atomic mass number of 12. So again, Let's take the first isotope of carbon-12 and we take the mass number and we multiply by the percentage of 99. Put it in brackets and we add it to the mass number of 13 up here, which is multiplied by its relative abundance, which is 0.9, and added to the final isotope of 14, multiplied by the abundance of 0.1. And again, we need to divide by 100 because the abundances are expressed as a percentage. And if we type that into our calculator, we get a number of 12.01. 12.01 rounded to the nearest whole number is 12, and that's why on our periodic table it's simply written as 12. Let's look at another example of lithium. Again, lithium has two common isotopes, lithium-6 and lithium-7. Lithium-6 has a 7.5% abundance and lithium-7 has a 92.5% abundance. If we write out our calculation, we can do the mass number of 6 multiplied by the percentage abundance of 7.5 and add that to the next mass number of the second isotope of 7 multiplied by 92.5%, divide by 100 because they are expressed as a percentage, and we get an answer of 6.9. So you will notice that on our periodic table, lithium has been rounded up to the nearest whole number of 7. But in fact, if we look at other periodic tables, such as this one, you will see that in fact, on a more detailed periodic table, lithium has in fact got a relative atomic mass number of 6.9. And that is because the periodic tables we are provided at GCSE are all rounded to the nearest whole numbers. The only exceptions to this are copper and chlorine, which we looked at earlier, which are given to a 0.5 decimal place. Now it's your turn. Use your calculator to answer the below questions and remember to show your working. Pause the slideshow and I will move on to the answers in a few moments. First, we need to take the percentage abundance of the first isotope with a mass number of 79. So we do 79 multiplied by 51, place it in brackets. So those two numbers there. And then for our second isotope, which is 49% exists as bromine 81, we just simply add that together and multiply those numbers. It's 49 multiplied by 81, divide by 100, and we get an answer of 79.9. Now on our periodic table, the relative atomic mass number would appear to be 80 on the GCSE periodic table. However, on a more detailed periodic table, we actually can see that bromine to 1 decimal place has a relative atomic mass number of 79.9. Question 2 is phrased a little bit differently. It says, in a sample of 100 atoms, 79 of them exist as one type of isotope. So we need to work out its percentage abundance. So what it's saying is that out of 100 atoms, 79 of them exist as one type of magnesium. So 79 out of 100 as a percentage, we simply can work it out like this, and we get 79%. With the other isotope, which exists as 10 of the atoms, we can do 10 over 100 times 100, and we get 10%. And finally, the other isotope, 11 of them out of the 100, exists like that, so that's going to obviously give us 11%. So this is of our magnesium 24, magnesium 25, and magnesium 26. So we can now use our percentage abundances to work out the relative atomic mass. So the next calculation, we need to do 79% multiplied by the mass number of 24 in brackets added to the 10% of the mass number of 25 plus the 11% of the mass number of 26. And if we put that into our calculator, over 100, we will get an answer of 24.32. Now on the periodic table, you can see that magnesium, in fact, with a more accurate periodic table, has a mass number of 24.3. On our periodic table, the GCSE one, it will be more like 24 rounded to a whole number. And finally, question 3, again asked in a slightly different way. In a sample of 200 grams this time, 181 grams is neon 20. So again, we need to work out the percentage abundance. And to do that, we just do a calculation that looks like this. So we're saying 181 out of 200 is neon 20. So to work that out as a percentage, we multiply by 100, and that will give us an answer of 90.5%, which is neon 20. For neon 22, we know 19 grams is present as neon 22, so we do 19 over 200, again multiply it by 100 to get it as a percentage, and we get 9.5%. And we can check we've done this right because both 90.5 and 9.5 need to add up to 100, and that is our neon 22. And to work out our relative atomic mass, we do our standard calculation from before. So we take our mass number of 20, multiply by its percentage abundance, which was 90.5, put it in brackets, add it to the mass number of 22 here, percentage abundance being 9.5, divide by 100, and we get an answer of 20.19. And again, if we look at the more accurate periodic table, we actually see that neon has a relative atomic mass of 20.2 because again, they have rounded up to the first decimal place, whereas on the GCSE periodic table, that is not the case. The next lesson in this unit is Lesson 9, Group 0, the Noble Gases. Thank you for listening to the GCSE Science Tutor. Please remember to like and subscribe to get further updates on lessons and tutorials.